This is the quiz one review lecture. How this is going to work is I have this whole, like all of these slides that are kind of a review of everything we've covered so far, but I'm not going to spend a ton of time on them. I put them all together so it's easier for you to find and study off of. But I mainly want to focus on doing some example problems. So start out. Important thing we learned, we're reminded of at least, was trig and how we use it in physics. We learned about displacement, how that's the change in position. Velocity, how it's the displacement divided by the time interval. And velocity is a vector, so it has a magnitude, which is speed and direction. Acceleration is the rate of change of velocity, and that's the change in velocity divided by the time interval. There's some strategies for finding the sign of acceleration. You need to know the direction of the motion, the direction of the velocity, and if the object is slowing down, speeding up, or moving at a constant speed. So if it's slowing down, velocity and acceleration are in opposite directions. Speeding up, they're in the same direction, and constant, there is no acceleration. Then we also worked on motion graphs. So here we have a position graph, and from a position graph, we can get a velocity graph, because the velocity graph is the slope of the position graph. So we can find the slope of this part. The slope of this chunk here is 0, so the velocity is 0. And then we can find the slope of that part. And using those, we can plot a velocity graph. And so here's what the velocity graph looks like. So that first chunk from 1 to 2 seconds, the slope was -2. Then it was 0, like we said. And then the bigger part was 5 meters per second. You can also get position from a velocity graph. It's the area under the curve or area under the graph. It's really kind of the area between the line and the 0 velocity line, this line here. So for example, if we were looking at from 1 to 3 seconds, what the displacement is, we would find the area between the 1 and 3 seconds on the graph. And then you can additionally go from velocity to acceleration, because acceleration is the slope of the velocity graph. So that's exactly the same as that first position graph, where you find the slope here. This slope is 0 because it's flat. And then you find this slope and you just plot those on an acceleration graph. We're going to do an example problem of this in a little bit, or after I go through the slide. Then we have our kinematics equations. I have them here in X and Y. Yeah, those are important. Now you know where to find them. And we learned the concept of free fall acceleration, which is really just acceleration due to gravity. And for us, that's -9.8 meters per second squared. We also learned about projectile motion. One of the main things with projectile motion was that our object is launched at an angle with an initial velocity. And so that means we have to break that velocity into the components in X and in Y. And what that tends to be in projectile motion, they'll usually give you this angle from the X. So that means that the X component is cosine and the Y component is sine. Another thing about projectile motion is how far the object goes, or the range, which is that horizontal distance, depends on the angle it's launched at. And to go the farthest, it needs to be launched at 45 degrees. That is what gives you the maximum range. Okay, then we learned about forces. So Newton's first law of motion says an object with no forces acting on it, if it is at rest, it will remain at rest, and if it is in motion, it will remain in motion. So what this really tells us is that a force is needed to change motion. It's going to stay the same unless a force is acting. Newton's second law said an object subject to multiple forces will undergo an acceleration. And from that, we got this equation where the net force is the mass times the acceleration. And that force also means the sum of the forces. So this is what we use to get our force equations. And then Newton's third law says that every force occurs as one member of an action-reaction pair of forces. The two members of an action-reaction pair act on two different objects. Remember, you can't have both forces in an action-reaction pair acting on the same object. They need to act on different objects. And they also point in opposite directions. So we have the example, the hammer exerts a force on the nail, and the nail exerts a force on the hammer. Then we also just covered friction. So static friction, remember, only as big as it needs to be to prevent motion. So that's why we have this version of the equation where the static friction force is less than or equal to the coefficient of static friction times the normal force. But then the maximum static friction force is equal to the coefficient times the normal force. And if you push harder than the maximum force, you're going to get the object to start moving. And when an object is moving, we have kinetic friction. Now, kinetic friction, it doesn't matter what the pushing force is or how fast it's going. There's just a constant value for the kinetic friction force, and that is the coefficient times the normal force. A couple other things with friction, the maximum static friction force is always going to be bigger than the kinetic friction force. So it's harder to get something moving than it is to stop it from moving. And that also shows up in that the coefficients of static friction are bigger than the coefficients of kinetic friction for the same objects. Then I have this table of force information. If there's an equation, it's here. If there's not, it just says no equation. And then just kind of when we use these forces. Also added pushing force at the end. It's not really like its own distinct force, but it is something that has come up for us. So I wanted to put it in the table. So these will be, I have an updated equation sheet for you that will be, or by the time you're watching this, it will have been uploaded already. So yeah, you will be able to refer to that for the quiz, or you can make your own also. So, there's kind of 4 sort of main topics we've gone over. Vectors, which kind of shows up in other places too, motion graphs, kinematics, and forces. And so if you feel like you need to practice any of those in particular, here are where you can find problems that we've already done to practice, plus for the motion graphs, because this was just a separate request, just another place where you can find motion graphs. These ones aren't going to look exactly like the ones we've been using because I haven't pulled the motion graphs from the textbook. But because I haven't pulled them from the textbook, that's a whole bunch of examples we haven't done yet. So for vectors, week 1, Tuesday activity, question 6, week 1 homework, question 4, all of the week 3 Monday post lecture. There was that entire week 3 Tuesday vector practice, and then question 1 on week 3 homework. Motion graphs, there was also an entire graphing practice assignment. So definitely go back over that, even if you completed it in the first place, if you feel like you need to practice motion graphs. Kinematics, a lot of what we've done has been kinematics, but there was one thing, the week 1 Thursday activity, what we were like, the ask in that activity was just for you to kind of interpret the problems. So now you could go back and solve those problems all the way. Anyway, so the things in parentheses is just telling you if it's only like specific questions or if it's the whole activity. So please refer to this if you need help figuring out which problems to practice. And now we will go over 3 examples. Okay, the first example problem we're going to do is from the week 3 Tuesday graphing practice, and it's question 3. So we have this velocity graph, and we want to draw the position and acceleration graphs that are associated with it. So remember, talked about we can get the displacement from the velocity graph by it being the area under the graph or under the curve. And then we can get the acceleration by taking the slope. So we're gonna do the position first. And one thing you need for a position graph, you need to know what the position is at time equals 0. And we can just say, and I just take this, unless the problem says, just assume that the initial position is 0, but you should write that somewhere. So anyway, we're going to say our initial position is 0, and then we can find the displacement at different points in time. So we'll just start with the first second. We'll just go by seconds since there's only 4 seconds anyway. We can make that work. So we have this little triangle that is, well, here, we'll say this is 0 seconds, that's 1 second. And this is 0 meters per second, and it goes up to 4 meters per second. So, let's see, we go up to 3, this one's 3 meters per second. So we have a rectangle. We'll take the area of the rectangle to be, one side is 1 second, and the other side is 3 meters per second. So that just gives us 3 meters as that displacement. But then we have this little triangle. And triangle, remember, is 1/2 the base times the height. So the base is 1 second and the height is 1 meter per second. So that gives us 0.5 meters. So the displacement here is 3.5 meters, displacement 1. And remember, displacement equals the final minus the initial. If we're looking for the final, it's gonna just be the displacement plus the initial. Since our initial here is 0, it tells us the position at x equals 1, or at time 1 second, is 3.5 meters. Now that'll be our initial position for the next one. So the next one is this kind of smaller. I'm going to end up drawing it the same size, but this only goes, this one, I believe, is 3. Yeah, this is 3 meters per second. This is 2 meters per second, 0. And still, let's see, this one is 1 second, that's 2 seconds. So we're just going to do the rectangle and triangle again, but this rectangle, at least, it's smaller. So the base is still 1 second, but it only goes up to 2 meters per second. So that just gives us 2 meters. And then the triangle is actually the same size. So it's 1/2, 1 second times 1 meter per second to give us 0.5 meters. So that gives us a displacement 2 of 2.5 meters. And then if we want position 2, it's going to be displacement 2 plus position 1. So 2.5 meters plus 3.5 meters gives us 6 meters for the position at 2 seconds. And then we just have 2 rectangles. So we have, this goes 2 meters per second, 0 meters per second, and this goes from 2 seconds to 3 seconds. So this area is 2 meters per second times 1 second to give us 2 meters. So that is our displacement at 3 seconds, 2 meters, and our position is that displacement plus the position at 2 seconds. So 2 meters plus 6 meters equals 8 meters. And then finally, the area of this one is going to be the same again. It's still going to go from 0 to 2 meters per second. And now we go from 3 seconds to 4 seconds. But those are still the same size for this side. 2 meters per second times 1 second is 2 meters, giving us the displacement at 4 seconds is 2 meters. And the position at 4 seconds is then the displacement plus the position at 3 seconds. So 2 meters plus 8 meters equals 10 meters for 4 seconds. Cool. So now we can plot that. Let's make a table just because it can make things a little easier. So we have time in seconds and the position in meters. So 0, we're at 0. At 1, we're at 3.5. 2, we are at, I think, 6. 3, we are at 8. And 4, we're at 10. Cool. So that's what we're going to plot. So we need to go from 0 to 10 on this axis. Let's see. 6, 8, 10. Cool. And we just need 4 seconds. We'll just do that. So time in seconds and position in meters. And then we just plot those points. Or actually, maybe I'll write what things are first. 2, 4, 2, 4, 6, 8, 10. There we go. So at 0, we're at 0. At 1 second, that's this one, we are at 3.5. Oh, wait, no, that's 3. So it would be right there. At 2 seconds, we're at 6. So right here. 3 seconds, we're at 8. And 4 seconds, we're at 10. So we kind of curve a little bit initially and then sort of straighten out. Okay, so there's our position graph. Then we want to do a acceleration graph. I'm just gonna copy the plot over and we can look at it on the next page. Okay, oh, no, paste. Here we go. Okay, so for an acceleration graph, we need the slope at different points. So first, let's start with the easiest. We can see that the slope from 2 to 4 seconds, slope from t equals 2 seconds to 4 seconds is 0. Because it's flat. The velocity isn't changing. There is no change in slope. And then if we go, we're working backwards now from 0 second to 2 seconds. Then we just want to do, so the acceleration is the rise over run, the slope. So the rise is the change in velocity and the run is the change in time. So for this, we start here at 0 seconds. We're at 4 meters per second. Oh, but this change in is final minus initial. So actually, we'll look here. We're at 2 meters per second, and then we subtract 4 meters per second because that's where we started. And then we go 2 seconds minus 0 seconds. So we get -2 meters per second divided by 2 seconds. So we get an acceleration here of -1 meter per second squared. So there we go. We have our two slopes. One is the one from 2 to 4 seconds is 0. The one from 0 to 2 seconds is -1 1. So let's draw that graph. 2, 4, and this is time in seconds. This is acceleration in meters per second squared. I'll just say that's 1, -1. So from 0 to 2 seconds, we're down here at -1. And then 2 to 4 seconds, we're at 0. Okay, cool. So that is our position and velocity graph. And remember, if you feel like you need more practice, there's a whole worksheet only on these. And also there's problems in your book that we haven't even tried yet. Now, let's do a kinematics example, specifically a projectile motion one. So we have a goalkeeper trying to kick a soccer ball into the opponent's goal without the ball touching the ground. And that is a distance of 95 meters. So we'll draw a little picture. We have our goalie, they're trying to kick this ball, and they want it to land in the other goal, a distance of 95 meters. 95 meters. And it says here, kick his goal, or kick the ball into the opponent's goal without the ball touching the ground. So that tells us that what we want actually is to know what the position is when it lands. And there's multiple ways we can find that. You could find the range, but we can also just use our kinematics equations. Let's write those down. Let's see. So, the final position in x is the initial plus the velocity in x times the time. Or maybe we should do time interval. And this one only works for x because acceleration, because x is has constant velocity. I don't know why it made there we go, my diagram went away. But actually, before we write the equations, let's do our knowns and unknowns. Let's do best practices here. Knowns. So, starts on the ground. So we'll say y initial equals 0. It also ends up on the ground, so y final also equals 0. We can say x initial equals 0. And then what else do we know? So if we're looking for the farthest possible distance that the goalkeeper can kick the ball, that tells us the angle needs to be 45 degrees. Because remember, the range or the total distance in x depends on that launch angle, and the maximum is 45 degrees. And we also have an initial velocity of 30 meters per second. And then we can say acceleration in y is -g. Acceleration in x is 0 meters per second squared. And unknowns. We don't know the total time. And we don't know the displacement in x. We're trying to find out if that's 95 meters or not. But if we look just at this equation here that I already wrote, it looks like we need to know the time in order to find the final position in x, which that's pretty typical for projectile motion. So now I'll write these equations in y to see which one will help us find the time. So v final equals v initial plus a y delta t. We don't know v final though, so y final equals y initial plus v initial y delta t plus 1/2 acceleration in y for the time interval. And v final squared equals v initial squared plus 2ay delta y. Okay, so let's look at our y equations. We don't know what the final velocity is. We know what the initial is. I mean, we haven't solved it yet, but we can find it. We have everything we need for that. We know what the acceleration is, but we don't know the time. We know this, and we know that. So this equation down here could give us the final velocity, but that's not what it's asked for. And then let's look at this equation. So we know the final and initial positions are the same. They're on the ground. We know the initial velocity. We don't know the time interval. We know the acceleration, and we don't know the time interval. So it looks like we can also just find the time interval from the long kinematics equation. So I think that's the best bet so that we don't have to solve extra equations. So let's look at the long kinematics equation. Y final equals Y initial plus V initial Y times delta T plus 1/2 acceleration in Y delta T squared. Oh, oops, look at that. I forgot the squared right there. Okay. So we know the initial and final positions in Y are 0. So we get that 0 equals V initial Y delta T plus 1/2 AY delta T squared. Both of these terms are multiplied by delta T, or the time interval, so we can divide one of those out. We can say that one's gone and that one's no longer squared. So we are at 0 equals the initial velocity in Y plus 1/2 the acceleration in Y times the time. Okay, cool, but actually we haven't established what the V initial in Y is. So let's draw this. So we have a V initial, which we do know is 30 meters per second. And we have this angle here that I said is 45 degrees. So we want to know what the Y component is, the initial Y. And while we're here, we should probably figure out what the X component is, V initial X. So V initial Y is, actually, let's start with V initial X is the cosine. It is adjacent to the angle. So it's V initial cosine theta. And that tells us that Y is V initial sine theta. Okay, so now we can put that in here. But first we should probably just solve for the time interval before we make our equation more complicated. So to do that, I'm going to subtract the initial Y from both sides. So we end up with the initial Y equals 1/2 acceleration in Y times the time interval. And then I'm going to divide 1/2 the acceleration in Y on both sides. So we end up with negative V initial Y equals 1/2 acceleration in Y. And that equals the time interval. Okay, so I'm going to move that over here, and then we'll put our equation for Y in there, and we have more information about our equation for the velocity in there, and we know more about acceleration in Y. So first up, we're just gonna plug that in, and we say V initial negative still sine theta divided by 1/2, and then we're gonna say this acceleration in Y is negative G. So these negatives cancel. Okay, and then we can just plug in our numbers. So we have 30 meters per second times sine of 45 degrees divided by 1/2 times 9.8 meters per second squared. I don't know if I'll just double check what I solved. 30 sine of 45 divided by 1/2 times. That gives us a time interval of 4.3 seconds. So let's see, going back to the equation in X, let's see what our position in X is after 4.3 seconds. Let's see if it is that 95 meters that we need. Pick a different color. So that's just, the equation is X final equals X initial plus V initial X delta T. And one thing we can say is that the initial position is 0. So this final position is V initial X times the time interval, which is V initial cosine theta times the time interval. That's 30 meters per second. Cosine of 5 degrees times 4.3 seconds. Let's check. 30 cosine 45 times 4.3. Yeah, nope. That puts us at 91 meters. So it is gonna hit the ground before he reaches, or before the ball reaches the goal. So bummer for the goalie. They can't kick it all the way to the other goal, which I mean, it's reasonable. That's a very far distance. But I just want to point out some things about projectile motion as a reminder. We could also find this maximum, oops, using the highlighter, maximum height here. And to find that, we just need to remember that the y velocity there is 0. So that's another thing we could find. But I'm not going to, we have another example problem to do. So now this one is from your week 5 homework, which is, when you're watching this, probably due tonight, Monday night. But I'm gonna solve this anyway, because yeah, I think it'll be good to see how we can do this sort of thing with things on an incline and friction. So we have 2 blocks attached by a rope passing over a pulley. They're each on their own incline, but the static coefficient of static friction between them and the incline is 0.3. Block 1 has a mass of 10 kilograms, and its incline is 23 degrees. And then block 2 has an incline of 40 degrees. But we want to know what the minimum mass of block 2 is that would keep the blocks at rest. So let's draw our free body diagrams at an angle. So this is for block 1, which is the 10 kilogram one. So we have the weight of block 1, normal force, which is perpendicular to the incline. We have the tension force. And then we'll just assume that our friction force is this way. Okay. And then we'll do, let's see, this one, I'm gonna try and get my angle a little better. Maybe that's closer to 40 degrees, who knows? This is theta 1. Okay, so this one's weight 2, theta 2, normal 2, tension is that way. And then the static friction force can also be down. Okay, cool. And remember, when we're on an incline, that means that we have to look at the x and y components of the weight force. I mean, when we tilt our axes and we're on an incline, if you don't tilt your axis, then the rest of your forces are going to need to be broken into components. So this is why we tilt the axes, so that only the one force needs that. So here's the y component, y1, and the x component, x1. Here, y2, and x2. And you can see for both of these, the y component is right next to or adjacent to the angle, so the y component is going to be cosine. So we will write these. Weight y1 equals weight 1 cosine theta 1, and weight x1 equals weight 1 sine theta 1. And then we have the same thing for 2. It's just want to write properly. 1 second. Weight 2. Weight 2 cosine theta 2 and x2. Weight 2 sine theta 2. Okay, so we know what those are now. Let's write our force equations. We'll start with block 1. And oh, I should write this actually. The net force for both of these is 0. We're looking for the smallest weight of block 2 or the smallest mass of block 2 that makes the net force 0. So net force Ny for block 1, 0. And in Y, in the positive direction, we have normal force 1. Negative Y, we have the Y component of the weight. So we subtract that. And then in X, still 0. And let's see, in the positive X, we have tension. And then we subtract the static friction force and the X component of the weight. Okay, now let's do this for block 2. Y2, 0. And this part is the same as the normal force minus the Y component of the weight. And then X2, also 0. This time though, the tension is in the negative X direction. So we have the X component of the weight plus the friction, static friction force minus the tension. Okay, so now what we're trying to find is the mass of block 2. And one thing we can do is we can get, well, right now we have, like if we're looking at this equation for block 2, for example, we don't know the weight or the friction or the tension, but weight and friction, the thing we don't know in there is the mass, and that's what we want to solve for, so okay. But we do have tension in this equation, and we do know the weight in both of these. I mean, we'll have to solve for it, but we can because we know the mass of the first block. We don't know this tension, but we can get rid of that. So we can go from 2 unknowns, or what looks like 3, but really it's just the mass that we don't know, down to 1. So we're just going to solve both of these equations for the tension and set them equal to each other. That way the tension is out of there and we don't have to worry about it. So for the first one, we're going to add the friction and the weight to the other side. So we get tension equals the friction minus the weight, or sorry, plus we added them to this side. And then for the other one, we're just going to add the tension to the other side. We get the weight plus the friction. So, okay, we can set those equations equal to each other, but we should also figure out what the friction is. So we're going to be working with our maximum static friction force, because when we're working on extremes like the minimum or maximum, it works in both ways. So we're looking for minimum mass, which means we're looking at maximum static friction force. So it's just the coefficient times the normal force. So we should solve for our normal forces here. So let's do that. We just need to add the weight to the other side. So normal force for block 1 is just the Y component of the weight in block 1, and the normal force for block 2 is the same thing as the Y component of the weight in 2. Okay, so now let's set these two equations equal, and then we can plug in our normal force equations too. So we have static friction 1 plus the weight and X component of the weight in 1 is equal to the weight X component of the weight in 2 plus the static friction. And then we'll plug in this and this. So the maximum static friction force equation and the normal force equation. So we get the static friction, or the coefficient of static friction times the normal force. So normal force for block 1 is just the weight of block 1 in Y. And then we have the weight of it in X. Then we have the weight of block 2 in X, and then the coefficient of static friction times the weight of 2 in Y. Okay, cool. So now let's pull in what weight is equal to, which is mg. because we're, again, solving for math 2. So let's actually get it in our equation. So mu s math 1 times g. And so this is the y component. So that one is cosine theta 1. And then math 1g sine theta 1. And this equals math 2g sine theta 2 plus coefficient mass 2g cosine theta 2. Okay, cool. Now we can cancel, everything is multiplied by g, so we can just cancel that out. Goodbye. And then on the right side of the equation, I'm going to factor out m2 because, again, that's what we're solving for. That just gives us sine theta 2 plus coefficient of static friction times cosine theta 2. We could do the same thing on the other side if we want and factor out mass 1. I mean, it doesn't do that much other than when we're plugging in our numbers, we only have to plug in mass 1 once instead of twice. So it's up to you. So now we can divide this thing in parentheses on both sides and solve for mass 2. So mass 1 times the coefficient in static friction times cosine theta 1 plus sine theta 1 divided by sine theta 2 plus coefficient of static friction cosine theta 2 is equal to mass 2. And then we'll just plug in our numbers. We're almost out of space. 10 kilograms and 0.3 for the coefficient, cosine of 23 degrees plus sine of 23 degrees. And then this whole thing divided by sine of 40 degrees plus 0.3 for the coefficient times cosine of 40 degrees for math 2. And what we, math 2. And what we get for this is 7.07 kilograms. So that is what we get for math 2 in this example. The main thing that we find with these force equations, like these force problems, the most thing I want you to kind of spend the most time getting comfortable with is drawing the free body diagrams and writing your force equations. And then after that, most of the rest is just like algebra. I mean, sometimes it's kind of complicated algebra, but that's the skill there. And so the thing that will help you going forward is being able to solve these, like knowing how to solve these problems. And to do that, you need to know how to draw free body diagrams and get your force equations from those diagrams specifically. Okay, I think I will leave it there. Feel free to reach out if you have more questions before you take the quiz.